So in our last example, we had too much ferrite, okay? We were hypoeutectoid. We had a carbon concentration that was less than 0.76%. So what happens to our properties, like our tensile strength, our yield strength, our ductility, if we are hypo or hypereutectoid? Well, it's not that hard to figure out. Think about it this way. Cementite is hard, okay? Ferrite is soft. And perlite's in the middle. So if I'm at that perfect eutectoid point and I start adding more soft stuff to go hypoeutectoid, well, obviously I'm going to have less strength and more ductility because it's softer. I'm adding more of the squishy stuff. It's squishy for metal. If I'm at the eutectoid point and I start adding more cementite, so I'm now hypereutectoid because I have more carbon, more cementite, well, I'm adding more of the hard stuff. And so obviously my strength increases, my hardness increases, and my ductility drops down pretty rapidly. So when I am hypoeutectoid, I am more ductile and less strong. When I am hypereutectoid, I am less ductile and more strong. Okay, so just basic things there. So you want to make it harder, stronger, increase your carbon content. Okay, now let's look at fine pearlite, coarse pearlite, and spheroidite. Okay, all of these. First off, if you're in that hypo region, well, eventually the ferrite's kind of taking over because you've gone too far away. But as we approach that eutectoid point, you see that the fine pearlite, for the same carbon concentration, is much, much stronger. Okay, it has much harder, and also that kind of corresponds with a much greater tensile strength, yield strength. On the other hand, it has a lower ductility, but the ductility has not dropped drastically, going from coarse to fine pearlite. So for fine pearlite, you're going to have high strength and just slightly less ductility. Now, an interesting thing is the spheroidite. This is where I heat it up to just below that transition temperature. Like I've already had perlite or something else. I heat it up just below the line to go to austenite. So I'm like right around here. And I keep it there for a while. And eventually, through interfacial diffusion, it's going to try to make nice little spheres. What you can see is spheroidite is much, much more ductile. Why is that? Because it doesn't have any stress concentrators. It's rounded all the edges. And its strength is still appreciable. It's lower than coarse and fine pearlite, but it's still very strong. It's way more ductile while also being fairly strong. So it's an overall great material. Okay, how about martensite? Martensite is way, way harder and much, much stronger, as in it has much higher tensile stress than fine pearlite, okay? It just goes off the charts here. You can see that. But it's very, very brittle. There's no point in us even showing the ductility because it does not want to stretch. You can just think of it as glass at this point. Glass is very, very hard. Glass has a very, very high tensile strength. But it doesn't want to stretch at all because it will just snap instantly. So, is there a way, like with the coarse pearlite and the fine pearlite and the bainite, to increase my ductility while also decreasing my tensile stress? Like, make it a little bit more flexible. And the answer is yes. We can have tempered martensite. How do we get this? The exact same way we got our spheroidite. So you make it 100% martensite, you heat it up for a while, and you let it reduce all those needles into small little circles. That reduces my stress concentrators, which decreases increases its ductility, but also those you don't have these long kind of like interlocking pieces anymore, and so its tensile strength has dropped. Okay, its tensile strength has dropped. So that's what we're doing here. You can see here that what temperature you heat it up to and hold it at is going to determine how much the properties change. And your tensile strength and yield strength drop pretty dramatically, but also your ductility does increase quite a bit as well. So you just have to choose what you're looking for. And the great thing is you can actually work to get the exact properties you want. You might make it 50% martensite and 50% something else, and then you'll temper it for a while and you can hone in on the exact tensile strength, yield strength, and ductility that you want for your particular use case. And once you've had that, you're golden. You've got it lock it in. That's what the next the next chapter is kind of about, is trying to figure out exactly how to hone in on those particular properties you want for a particular iron carbon alloy. Okay, that's it for this time. Thank you so much. See y'all later. Bye-bye.